finding the optimal solution. That means it's important, yeah, to do the optimization problems. Yeah, and we will try to do simple problems to get the idea, yeah, maximizing the volume, profit, minimizing distance, time, cost, of course. And in general, what we have to do, we have to find the extreme values of the function. Probably we will have a scenario, we will have like a word problems. We have to figure out what they asking us, maximize or minimize. And then we have to build a function, build a model which fit to the scenario. Having a function, probably one variable will be helpful because we are still not in calculus 3 for 2 variables function, one variable function, and then we will set up the domain, the set of X that makes sense, like what is our like platform environment. And then on that domain, we will try to find the absolute maximum or absolute minimum, depends what they're asking. If a domain is an open interval, like we're not including the endpoints, then the local extreme values will become absolute extreme values. If the interval, of course, we still have to check a couple of conditions, but that's usually what will happen. If the interval is closed, we also remember what we have to do. Finding a locally highest or lowest point, that's one thing, but we also have to check the endpoints, because maybe the end of the domain, the end values will give us higher value or lower value. Yeah? The extreme value, like theorem, finding the values on the closed interval. Okay, too much theoretical part. We can see, finding the critical values, maybe the endpoints, and evaluating which one is the largest, which one is the smallest, depends what they're asking. In general, finding the minimum or maximum value of the function. Okay, I typed a couple of steps, which of course, it's always the same steps. If you will look at the related rates, similar guidelines I was providing, like read and understand the problem. Of course, understand is not really measurable word, because understanding things means it has lots of meaning. Yeah, but we know what this means. We have to read carefully and try to understand the scenario. Draw some diagram, some picture. Yeah? Of course, if possible. As soon as we have a diagram, as soon as we have a picture, we can introduce some notations, labels, yeah, X, Y, Z, because we need this. And as always, we have to look what they're asking, and I mean what they're giving us, what is given, what is required. Yeah? And then determine whether we're maximizing or minimizing, because this will be not stated directly. Yeah? Sometimes we may have, you will see actually, like, what will be the cost to build the most economical box, for example. We need a material to build the box. We have a special given condition, but what are the dimension for the box to build a most economical box? This, actually what this will indicate, we will maximize or minimize everything. Yeah, because we would like to build the box as economical as possible. We would like to minimize everything, to spend like less money on the material. Yeah? Most economical, of course, the cheapest container, cheapest box, minimum. Yeah, that's how we can translate the words. And then we will build a function. We have to find a function of one variable, of course. We will need some relations, some connections, and relation connections to have the variable. And then we have to determine where we are, the domain. Yeah? And then differentiate, because we have to find the derivative for the critical points, and test for the maximum, minimum, test the extreme values. And always answering the question, check, double check because we have the whole process, and sometimes we even forgot what they're asking. Are they asking for the dimension of the box, or actually they asking for the minimum area? Yeah. Then we can always get back to the beginning, read the question and answer, because we will have all of the information. Okay, let's do it. Couple of questions. That's the first derivative. That's the open and closed interval. And oh, I can show you in a minute. Okay, typical, beautiful question. A farmer has 2,400 feet of fencing, and he wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? Okay, do you think you can tell me, are we going to maximize something or minimize? That's what I said. Yes, we will not have directly. We're looking for he wants to have the largest area. Similar like this land on Manhattan. We want to maximize the area. Yeah, largest area means the maximum area. Let's actually look. I have this possible graphs. I don't know, he doesn't need a fence along the river. Maybe he will put 100, 100 and 2,200, maybe 1,000, 1,000 and 400, 700, 10,000 and 700. Of course, we will another step will be to compute that areas, but we will not compute like multiple, like infinitely many areas. No, no, no. We will build a rectangle, we will label with unknowns x and y, and now we can go from there. We will build a function, we will build a model that depends on the length and width. Okay, let's see given and required. Okay, I copy that picture. Okay, given information is this parameter 2,400. Okay, now we will need a formula. We will need a formula actually. Oh, okay, for this parameter, and we can see 2x, 2 x's, and 1 y. And 2x plus y actually equals to, okay, I will, this 2x plus y, of course, is the same like 2,400. We did have proper equation, proper given information. Okay, but I type the required. As we just stated, we have to maximize the area. To be maximized, yeah? Find the largest area. Of course, to find the largest area, we need a formula. Can you tell me what is the formula for the area of the rectangle? Just simply base times height, x times y, x times y. But we can see, because we will focus on this function, but we need a function which depends on one variable only, x or y. We can pick x. X is always the standard one. Okay, x and x or y. Now we will use this given statement, given information. Actually, we create the statement. We create this equation. But 2,400 was given, and we may solve this for y. 2,400 minus 2x. That's how y depends on x with respect to the restriction of 2,400 feet of fencing. And we can take this and substitute instead of y. That's our function to be maximized. Of course, I can distribute to avoid product 2,400 x minus 2x squared. And we will use calculus, but we can also look at this. This is quadratic function. Leading coefficient is negative. Parabola, open, down. Yeah, that's the graph of the function. Definitely this function is attaining maximum, and we're looking for that x. Right? And this indicates that the local maximum will be the absolute maximum. We can also find the domain, right? Because we also have to find the domain. Not all of the positive x are the domain. Of course, X and Y is positive. That's not even the question, because that's the length, positive. But what we also have, oh, too fast. Let me, I did type it. Okay, I can maybe remove it later. We do have this restriction, right? Because Y is defined as a 2400 minus 2X, because we cannot have longer. If X will be any number, let's see this. Any big number times 2 will give us negative 2400. We cannot have bigger than 2400, that product. That means this quantity must be positive. That's the restriction, that's the domain. And when we solve this, okay, and then divide by -2, the inequality will change the sign. And of course, X is also positive. X cannot be greater than 1200. Not even exactly 1200, because then we will not, like we will put 1200 and 1200, we will have no, like if I will put 1200 and 1200, we will have no fence left for Y, right? And since it's the open interval, that's of course the same thing, just, and function goes like definitely down. Like, oh, at infinity, for the big numbers, if we would like to find the end behavior, function is definitely going down, getting lower values. Local extreme, local maximum will be the absolute maximum. That's what we're looking for. Okay, let's find this local absolute value. We need a derivative for the critical points. I did compute the derivative. And now derivative is 0 if 2400 minus 4x is 0. Let's solve it. Oh, now I have the domain. Probably my timing, okay. That's interesting. I did remove it, my writing, and I didn't type. Okay. X is, of course, positive. Domain is between 0 and 1200. That's the X values, because we cannot have negative Y. Okay, now, so let's find the critical point. We will divide 2400 by 4, 600. Okay, X is 600. I can place on the number line, and we will test, because we know based on the shape of the function. But let's just use the first derivative test. If I will substitute 1, of course it's positive. And when I substitute like 1000, 4 minus 1000, I mean 4 times 1000, let's say 1000, will be 4000 minus negative greater than 2400, negative number. Derivative behaves like this. This is just the derivative, right? Derivative. And then function, the area is increasing and then decreasing. Of course, we can nicely see local maximum, and this is absolute maximum at X equals to 600. Okay, 600. Now let's compute the Y. If X is 600, 2 times 600, 1200, 1200. Okay, if X is 600, Y is 1200, that's the maximum area. And now let's come back to the question, what are the dimensions? Oh, dimension, just the dimensions. Okay, we can say 600 by 1200. That's the dimension. I thought that we have to multiply them together to find the area, but no. What are the dimensions? And we can see we have everything done. Okay, let's do another question. Oh, okay, let's try. An open rectangular box with a square base is to be made from 48 square feet of material. What dimensions will result in a box with a largest possible volume. Okay, largest possible volume. Okay, the area, the surface area is provided. We do have a box, open rectangular box. I can label X and X because the square is in the base, and I can name it height. Okay, step by step. We have no top because it's open. 48 is simply the surface area. Like how we can build, we need that 48 square feet of materials. And in order to build this, we will need the base, which is X times X, X squared, and we need 4 sides. X times Y, X times H, another X times H, another X times H, we don't see, maybe that is square, and the back side, X times H. We do have 4 walls, X times H, base times height. X squared plus 4 times X times H. We can see that's the next step. We have to take care of the given information. And we may like set up an equation. X squared plus 4xh. Am I doing this? No, I'm not. I'm doing the required information. X squared plus 4xh equals to 48. And we may solve it for x or for y, for x or for h, depends what we decided. Probably for h, because you can see x squared and x, it will be challenged. Because we need to rewrite one variable in terms of the other and check, yes, what we need for the required information. Okay, largest possible volume. Volume, we have to maximize the volume. We will set up the formula that represents the volume of this box. We will try to make it one variable function, and then critical points, maximum, minimum. But in this case, we need maximum, largest possible volume. Okay, volume is length times width times height, x times h, x squared times h. And of course, we need one variable. We will set up this equation and we will solve for h. H simply equals to this, and we will substitute instead of h. 48 minus x squared over 4x. And we can simplify. Let's see, okay, we will take care of the volume, but of course, let's look at the domain. Let's look at the domain. Domain, again, x and h is positive, not, yes, because we cannot have negative length. And theoretically, denominator 4 times x could be any positive number. But we have to be careful for this. We do again, that 48 is giving us some restriction. X squared cannot be greater than 48. Because if x squared is greater than 48, we have subtraction. We will produce the negative number. Right? It means 48 minus x squared must be greater than 0. And I think I factor out this way. And when we will look, like because we can also solve this inequality through the zeros, square root of 48 and negative and positive. And when we will test, actually we can look at this form, quadratic equation, parabola, open down, because it's leading coefficient negative. This is giving us negative values. We're not looking for this negative, positive. And we cannot take the entire interval because this interval includes negative numbers just from 0. From 0 to square root of 48. This is the only option for x. And still open interval. And this goes down. It will be, all of the values will be lower. The local absolute value will be the local extreme local maximum, that's what I was going to say, local maximum value will give us absolute maximum. That's what I wanted to say. Okay, x cannot be outside this interval, and this, of course, meaning that square root of 48 is the maximum. I mean, we can't even include this one as an open interval, because if x is 48 minus x squared, if we will put square root of 48 and squared is 48, 0, we cannot have 0. And that's we're not even including the endpoints. And since we're not including the endpoints, again, the local extreme values will be the absolute extreme values. Okay, let's take care of the function v, and let's find critical points and the local absolute. Oh, why? Because I want local maximum, which will be the absolute maximum. Okay, what we have? We do have x and x, we can cancel out, and I believe we can distribute x times 48 and x squared times x cubed. And 4 in the denominator is okay, it's just the constant. Okay, did I divide it? Oh no, I didn't divide this. Okay, this is our function, 48x minus x cubed. Now we need the derivative. And this is, we can see, is the cubic function, x cubed with the negative. When x is bigger, the values are lower. That means, again, the local maximum will be absolute maximum. Now I didn't make the mistake in my sentence. Okay, let's find the critical point. We need the derivative for the critical points. Derivative of 48x, I can remove that. It's 48. Derivative of x cubed is negative 3x. And this is just 1/4. This is just the constant. I copy a constant 1/4. And now derivative is 0 if the numerator is 0, because denominator with being constant is never 0. Okay, let's solve it. Oh, it will be not nice number, or maybe, oh no, it is nice number. I thought again that we will have, because we can divide by 3, 48 is 16, square root of 16 is 4. Normally we will have -4 and +4, but we're not accepting negative numbers. And we can try to test the v prime. V prime is actually this formula. When we substitute like 1, or even 1, we will have positive number. When I substitute like 5, 25, 3 minus 48 minus 3 times 25, negative. Increasing, decreasing. Of course, maximum. Local maximum, but all of the values go down. This is absolute maximum when x is 4. Okay, but again, what is the question? What dimension? Okay, that means x is 4, 4 by 4, and we need height. And we can compute height. How we can compute height? We can substitute 4. 48 x squared, 4 squared over 4. Oh, 4 times 4. Wow, it's x. Okay, let's try. 48 minus 16, it's 32. 32 divided by 16 is 2. H is 2. That means it's actually to get the most, the largest, to maximize, this is x times, oh no, I will remove that x because my x's sounds, okay, 4 by 4 by 2. It's relatively short, yes? To maximize the volume, the box will be like shorter because height is only 2 feet, 4 by 4 by 2. Okay. And we can see the same scenario. Okay, let's try maybe 2 more. you have the solution for this one. Oh, let's find this one. That's a nice question. Find a point on the line y equals to 4x plus 7 that is closest to the origin. Oh, okay. Okay, and we can see quite short instruction and information. The only given information is that equation of the line, 4x plus 7. Slope is 4, y-intercept is 7. And what we have to find out, find the point on the line that is closest to the origin. Okay, now we have to translate this. Closest means that the distance is minimum. Okay. Oh, I didn't. I would like to draw it. That's what I thought that I didn't. Okay, 4x. I don't know if this is a good. This is 7. This will be negative 7 over 4. A little bit too small. But okay. And we do have the origin. And we would like to find out that point, x and y. Okay, that green, because that's, I'm guessing, that's the shortest distance. And we don't know. It's probably going to be some fraction, question mark, question mark. Of course, we can see right away that the numbers will be, the y value will be not greater than 7, and the x value will be not like smaller than negative 7 over 4. Okay? That means this is that y value and this is that x value. Okay, we have to find out this point. We will need a distance formula for this question. And I type the distance formula, x2 minus x1 squared plus y2 minus y1. Yeah? Let's substitute our points, x minus 0 squared, y minus 0. Because 0, 0 is the origin and x, y is our point. Of course, we don't need the zeros. Okay, that means this is our function, distance. We have to minimize this function. But what is also interesting, to minimize the square root is just enough if we will minimize the quantity under the square root. Because if the quantity under the square root is like as small as possible, square root of it is also as small as possible. And that's what we will do. Oh, too fast, too fast. We will just focus on the inner function. Here we have to minimize the inner function. Okay, that's it. That's we will see in a minute. But what is also, we know based on the previous questions and based on the guidelines, x and y. Yeah? We don't know exactly how to deal with the function of two variables. We have to rewrite in terms of one variable. And perfect, because the given information is the relation of y with respect to x. We can simply replace y with 4x plus 7. That is that's the function, because x, actually y, satisfies this equation, 4x plus 7. The point is placed on that line. Okay, and now that's what I wanted to do. We can see, to be like mathematically correct, I square both sides. That means instead of like having a function d, I will simply have function d squared. Yeah? We're not doing anything like this, is just the name, d squared. Because what I'm trying to do, I'm trying to minimize the quantity inside. Okay. Yeah, in this case, we can see domain. Domain is like, theoretically, x could be any number and y could be any number. But we will not, the big numbers will give us extreme. Yeah? We need the critical point of this function. Okay? We need the critical point, because the critical point will provide the local extreme values, and the local extreme values actually are the absolute extreme values. Okay, for the critical points, we need the derivative. Oh yeah, I'm just trying to. Derivative is as follows. D squared, d squared is our name of the function, d squared prime. That's the derivative. X squared is 2x. 4x plus 7 squared, it will be 2 times 4x plus 7 times 4, derivative of the inner function. Okay, when we distribute everything, we will get 32x plus 2, 34x, 8 times 7, 56. This has to be equal 0, okay, for the critical points. And subtracting 56, dividing by 34, and just dividing by 2 each of the quantity. And now I think 17 is a prime number. We cannot divide further. Negative 28 over 17. And I believe this number is, I know it, I knew it, that it's weird, but this number is definitely somewhere here. Right? This number is here. Okay, that's mean x equals to, oh, blue, okay. X equals to negative 28 over 7. Over 17. And now we just have to find the y value. Did I compute? Oh, I didn't compute the y value. Oh, no. Relax. We have to prove it that is minimum. Oh, no. Let's do it. The first derivative test. Negative 28 over 17. Where is the derivative? I believe this is a good formula. Okay, that's the derivative, d squared, derivative. When I substitute what number? Let's say negative 3. When we substitute negative 3, we will have bigger number than 56 times 30. It will be negative. And when we substitute even 0, it's a good testing point. 34 times 0 plus 56, it's positive. And then function is decreasing, increasing. We definitely see a local minimum. But this is also, since function is, this will be also the absolute minimum. So yes, this is good number to minimize the distance. The only thing is we also need y. Y is defined as a 4 times x plus 7. Negative 28 plus 17. But let's just leave it. I will skip the arithmetic because I don't like 28 over 17, negative 28 over 17. We can do it, but no, the green boxes are that's the point, x and y. And definitely the distance will be the shortest. I only hope that this y value is less than 7. It will be less than 7 because we can see this is 7 and we're subtracting. Yeah, subtracting the number. Okay, maybe one more. Let's do one more because I don't want you to do. This is the matter, but let me just check something really quickly. Yeah, that's the crazy. Okay, no. Let's don't do the price. We have the same question that we just did. Maybe we can do this one. Or maybe we can do, actually, let's do both. Okay, let's do both. Because both of them, this one is good and this one is good. Let's try. Yeah, we will not go so crazy with this. Definitely the distance is a good question, okay? For the final test. Okay, the same question. Find the x coordinates of the points on the parabola x squared minus 3 closest to the origin. Okay, let's see. I didn't type the solution, which is maybe also good. That's parabola shifted 3 units down. This is square root of. And now we're looking for, this is origin. And you can see what's happened. This is symmetric. We will probably have that point and this one. Yeah? And the good thing is we just need the x value. What are the x values? Right? And I will assume, or maybe it's even this point, I don't know. But we will have 2 points. I mean, this is not good answer and this is not good answer. We need, since parabola is even function, it's symmetric with respect to y. Okay, let's just name it xy, xy, and let's follow the same thing. We will minimize the distance. Distance formula is x2 minus x sub 1 squared, y sub 2 minus y sub 1 squared. Of course, one point is 0, one point is x, y. X minus 0 and y minus 0. And let's square it, because we will focus just on the squared. X squared plus y squared. Okay, let's rewrite this distance in terms of, because this is our function, but we need one variable. I will keep x squared, and from that expression, from that formula of the parabola, I can solve it for x squared, and it will be y plus 3. That's what we will do. Oh, actually, okay, because it's easier, actually, I will rewrite function in terms of y. X squared is y plus 3 and plus y squared. We don't have to square it because that's the x squared. Okay, looks like a good function. Let's make a nice order. Y squared, yeah, this is just the name. Yeah? Please do not we will not use that square. No, it's just the name. Y squared plus y plus 3. And again, function goes, parabola goes up. Theoretically, any number could be in the domain, but we know that this local local extreme values will give us absolute extreme values. Parabola, of course, for the d squared. Let's find the critical points. I can maybe do this. We need the derivative. 2y plus 1. Oh, okay. 2y plus 1. Am I right? Okay, yes, yeah, I think looks okay. For the critical points, we will need derivative to be 0. 2y plus 1 must be 0. Y is negative 1/2. Okay, that's we got negative 1/2 for y, but we need the x values. But let's double check. Negative 1/2, and I will test the derivative. This is derivative. My function was d squared derivative. When we substitute, let's say negative 1, 2 times negative 1 plus 1 is negative. And when we substitute 0, is actually positive 1. Function is decreasing, increasing. Of course, local minimum, but it will be also absolute minimum because all of the values goes up. That's the lowest point on the graph. Okay, y, actually this is y, y equals to negative 1/2 is giving us minimum. Then we have to compute x. Okay, x squared equals to y plus 3. Let's just substitute. Negative 1/2 plus 3, of course, is 5/2, and taking the square root, we will have that option. Positive and negative square root of 5/2. And yeah, makes sense. This is negative 1/2, and this will be positive, and negative square root of 5/2. I can remove that 0, 0, because we know this will be 5/2. I'm just trying to organize, and this is of course 0, 0. Okay, nice exam type question. I think so. Of course, you will probably, I hope not, but to save time, maybe you will skip the first derivative test, but it's also worth it to check. And you probably realize as soon as we asking to maximize something, the maximum is the only extreme values. If we asking to minimize, the only critical value will give us that minimum. Also good pattern. Okay, the last question for today, and that's how we finalize the optimization. And I just would like to tell you that please, we will not go so crazy, because I know that we always afraid about the word problems. The types of the problems that I solved today, that's the types that we have to focus, okay? And you can also check the homework assignment. That's only the types of the question, okay, that you may see again. Okay? No other options. The distance is a good question. Okay, let's see this. According to the postal regulation, a box is classified as oversized if the sum of its height and girth, parameter of its base, okay, the parameter of its base and the height exceed 108 inches. Okay, that's 108 inches is the maximum. We cannot exceed 108. For a box that has a square base and it's not oversized and has the maximum volume, find the length B of one side of the base. Okay, we just have to find the length of a base, yeah, the side of the base of the box that is not oversized and has the maximum volume. Okay, we have to maximize volume. Okay. What I will do, the sum of its height and the parameter. Sum height plus 4 times base, it's 108. This will be our restriction. Height is basically 108 minus 4b. We can see that's the given information. And now volume is base, length times width times height. B squared times height. But height, we need in terms of the B, because we need one variable function, 108 minus 4B. Volume, it's defined as a 108. B squared, I'm distributing this. B squared minus 4B cubed. Perfect. We did manage to have a volume. And again, volume is, we do have some restriction because height must be positive. I'm just trying to figure out the domain. Positive, negative 4b must be greater than negative 108, dividing by negative 4. 108 divided by 4, 54. 27. Yes, 27. Okay, that means B must be less than 27 inches. Right? That means this is our domain. And that we can guess that this will be not a good answer, because it will be oversized if this will be equal to, must be less than 27. Okay, and now looking again at the volume formula, it's the B cube negative. It will go down. We have to maximize the volume, then critical point and the local maximum, it will be absolute maximum. Okay, for the critical numbers, we need the derivative. Derivative of 108b squared is 216b minus 12b squared. Okay, derivative is 0 if 216b minus 12b squared equals to 0. Let's factor out b. Probably, okay, let's factor 2b. 108 minus 6b. Am I right? I'm just trying to. Then this is giving us 0. 0 is not a good number. And this will give us 108 divided by 6. 108 divided by 6. what we can do. Divide by 2, 54, divide by 3. We can do, what is 54 divided by 3? 18. I think it's, yeah, thank you, thank you. I thought that I lost my students completely. Yes, 18, I think it's too, too long. Yes, it is 18. Okay, let's do a little bit nicer from that. To get 0, it is 18. Okay, and probably 18 is the good answer, just to be sure. Oh, actually, this is B. We can place 18 and we can test the sign. Let's do this of the derivative. If we will put 0, I mean 1, because we are not allowed to put 0. 1, we will get positive. And if when I put huge number, like let's say 1,000, we will have negative value. Then volume is increasing, decreasing. We will have local maximum for 18. At 18 inches is also the absolute. Okay, this is the correct answer, 18. Okay, because we just, also a nice question. Okay, that means just to finalize, we have to find a function with one variable, find the critical points, test the points, and most likely the one critical number will give us maximum or minimum. That's what is required. And to get one variable function, we're always using the given information to rewrite the other variables.